Hey there, code enthusiasts. Welcome back to Conquering the JavaScript Interview. Today, I'm going to be shifting gears. That's a shifting gear noise if you didn't know. To explore the world of, and also, why am I shifting gears with my left hand? This is a terrible intro, so let's get back to it. You might think it's all zeros and ones in bit manipulation, but there's an immense amount of power in those bits, and we're going to try and unlock it here together. Before we start flipping any bits whatsoever, remember there's a link down below in our description for our community membership here at Covalence. It's just $25 a month, and it grants you access to over 300 hours of full stack content, which is, again, our entire full stack program broken down into 2 smaller courses, my entire comprehensive React course, Discord, and any new courses and updates of those courses are just handed to you for free in that membership. So it's your all-access pass to continuous learning in the evolving landscape of web development with a supportive and positive community. With the plus side being, you can bother me for video content ideas or things you might want to see done. Back to it though. In this session, we're going to tackle bit manipulation techniques. Now, this little mini-series, kind of like my Array Architects mini-series, this little Bitwise Operations mini-series is going to be taking a closer look at these, and in this video and others, I'll do some explaining of what they are, their purposes, and things like that. So these were pretty much magic to me, and I've been coding for like 6 or 7 years now, and they still feel like magic to me, but I've begun to understand them, and this last week and a half or 2 weeks of deep diving this content, I've tried to put together a simple explanation of how to begin to look at them and use them, and I think I found a very simple way to do so. So it can not only super speed your code, it can also significantly reduce complexity so long as you understand them. Nevertheless, you're going to be able to flex in an interview should you encounter this, because remember, luck is where opportunity meets preparation. So we're going to prepare to learn these bitwise operators and how and where they can and can't help us. And if you see the opportunity to use it, dang, you are going to look good. So buckle up and let's get bitwise. So bit manipulation involves using bitwise operators to directly manipulate one or more bits of binary data. Let me say that again. Binary data. It's extraordinarily fast, memory efficient, and can perform some operations in fewer lines of code than their higher level counterparts. So today we're going to be doing a very simple algorithm called findNonRepeating element with XOR, aka the exclusive OR. You're going to hear me calling it the XOR operator or XOR operator. Z-O-R is how I'm going to pronounce it. So that's what that XOR stands for in that little CodePen prompt right there, which, oh, by the way, you can go grab this from the CodePen in the description down below. I have a link to it. You can grab the prompt and try solving it yourself or following along with me, but you're going to see how simple it actually is. The following along part is understanding how it works, not writing the code itself, because you'll be surprised how simple this is. So like I said, it's a sleek function with an efficient solution designed specifically for arrays where every element except one repeats an even number of times. That is a big part of the note right there, right? So this is, think of like having a drawer full of socks where each sock has a pair except for one sock that might be like a patterned or dress sock that got into your sock drawer if you're that meticulous about organizing it like my wife and I are. But so that's the big note. If you see an array of evenly repeating numbers except for one straggler, then this solution will be extraordinarily memory efficient, speed efficient, very elegant, and will give you the chance to show your interviewer that you really know what you're doing. So again, preparation plus opportunity equals luck. In our case, good luck. So in the new year here, I'm going to go ahead and get to coding faster and not spend 20 minutes talking anymore. So we're going to go ahead and write out the code for this particular solution. So like I said, function, findNonRepeating. We're given an array of numbers. We're going to make the assumption that they are going to be one odd number out in an otherwise even number of repeats. Now, it doesn't have to be 2 repeats. They have to be even. So as long as I have a couple of 7, if I have like 4 9s and 6 7s, that's fine. As long as they repeat is the important part, right? So just like in the simple example up here, 1 appears twice, 2 appears twice, 3 is the odd individual out, the odd number out, which means we can pick it out easily with this solution here. So that's the big key to remember. This will fail if we have an odd number of pairs, for example. So here we go. First things first. I'll be tracking a result number here. So in a traditional solution, maybe you would do like a number map where you would generate an object where each key of the object is the number in the series, and the value is how many times it appears. So one appears twice, 2 appears twice, and 3 appears 1 time. So you would loop through this input array, map out the numbers and their appearances. Again, the keys are the numbers that appear. The value of them is how many times they appear, and you would simply loop through this object and find the key that has a 1 in it, which means, boom, you have found the single appearing number, right? But in our case, we're going to do things a little bit differently. So instead of having to run 2 for loops and an object, we're going to do vondi const num. Again, my keyboard shifts around my mat depending on what I'm doing throughout the day. So you can always tell when I've been gaming before this video because my keyboard has moved to the left, so my home keys are shifted over. So yeah, dead giveaway, I'm not working. What a surprise. So we're going to have this right here. So I haven't told you what it is yet because I'm trying to blow your minds here. That right there, not the equal sign, but rather the up caret, shift 6, whatever that, I should have looked this up. It's up caret, right? Or is it up dog? What is up dog? Yeah, okay, it's called a caret. I thought so. An upward pointing arrow is basically, right? It signifies a number of different things. And in our case, the up pointing caret is our XOR operator, exclusive OR. So right now, all we're going to do is do a reassignment. Remember, this is a shorthand. Don't get confused now. It says result equals whatever result currently is with a XOR bitwise operation on the current number of the array we're looking at, and it reassigns itself. So that's all that shorthand is right there, okay? And then all we got to do is return the result. And believe it or not, that's it. Let's go ahead and do a quick console log test here. I'm going to go ahead and throw that in there. That way I can comment it out easier later. Let's go ahead and grab my first example, and we're going to try and break down how this works afterwards. But yes, surprise, surprise, in that series of numbers, 3 is the result. So I was actually really excited to code this out and basically blow y'all's minds. So anyone watching is just like, Luke, bro, what is this? This is insanity. This does not make sense. You're like, you said this is going to be elegant. I mean, it is elegant if you know what it's doing. So this is great. This is so awesome that I feel like I've finally began to understand these things at a fundamental level, and I was so excited to put together this video and make a little mini series that builds out this as an example. Where's my diagram? There we go. We'll get to that in just a moment. So, yeah, there you go. That's the solution. Now we're going to spend the rest of the time describing how this actually works, and I'm going to write out each iteration of this particular solution. And by the way, the placement of the 3, the order does not matter. Remember, that order is not important. It will still result 3 once I save and refresh the console log there. It still outputs the correct value. Like I said, it fails when you don't have even pairs. So if I add an additional 1, we get the wrong result. That's okay, right? That's why you have to be very cognizant of your inputs. So if your interviewer gives you this example, maybe it's a test to see if you know this or something like that, you got a very awesome solution. And now I want to be able to tell you why it works. So all we do is initialize a variable called result to a value of 0. We're going to iterate through the array, and we're going to use the XOR operator on result and each number. So we are going to learn that XORing a number with itself cancels itself out. So we're only left with the non-repeating number. That's the whole magic behind this, right? It's because every time you XOR a number with 0, it's the number itself. So the single non-repeated number is what we're left with. So basically, this whole operation works because a number XORed with itself is basically canceling itself out. So the 1s will cancel themselves out, the 2s will cancel themselves out, and our remaining value and result will be 3. That's how this whole thing works. That's the TLDR. If nothing else, if you memorize how to write this, the caret, that's it, and you have clarified with your interviewer or the person you're chatting with, or just to yourself because you love learning like I do, then okay, if I see a input array that looks like this, that has a set of repeating numbers that are even with one that's an odd man out, then I can very quickly and easily use this bitwise XOR operator to cancel all pairs of numbers out with each other. Therefore, I am only left with the one that cannot cancel itself out, aka the odd number out, and booyah. And by odd number, I mean the one that's not in the list, right? So meaning, right? It doesn't have to be an odd number like 3 or 5 like I just showed you. 6 is the odd number out because it doesn't have a pair inside of this non-repeating number. So that's what I wanted to point out here. Okay, it's not that literally it's an odd number. It's the one that's not in the repetition here in my input array. But there you go. So, all right. All this aside, I think everyone's response is like me when I finally got this, which is, yo, what? So let me do some backtracking here. Like I said, I'm trying to do more code up front and less talking up front. But now it's the talking part because y'all need to understand what's happening here. So first off, what are bitwise operators? You might have been a front-end or back-end dev for quite some time, and you may have never even encountered one of these before. So what are they? They are functions that operate on binary integers at the level of their individual bits. Remember, bits, zeros, and ones. That's what you think of when you think of binary. So those individual zeros and ones that make up a number or things or data on a computer, they're zeros and ones, aka individual bits. We've got several types that do things for us. We have the XOR, which is that caret, but we also have a few more. For example, we also have other operations such as we have XOR, so we know what XOR is. We have AND, which is our single ampersand. We have OR, which is our single straight pipe. And then we also have our NOT operator, which I believe is tilde. Then we saw the XOR, which is our caret. And then we have two that are called shift operators, right? So these are called shift operators. And they're two separate ones right here. They're two different, they're not like a set of tags that are encompassing something in the middle. They're two different ones, right? So we have the two less thans and the two greater thans together make up the shift bitwise operator, right? Because you can shift things left and right. Surprise, surprise, like the name implies. Okay, so that's the other ones that we have here, right? So the whole thing is that each one can take your binary data and it can morph it in a unique way following rules of binary arithmetic. So if you're not too sure what that is, don't worry, I'll get to that in a second. Just keep on up, right? So that's our technical definition. They a set of functions that operate on binary integers at the level of their bits. They take data, binary data, and morph it in a unique way following the rules of binary arithmetic. Now, what does that mean in plain English, right, Luke? That's what you brought. All right, Luke, tell me in English. Imagine you've got a string of Christmas tree lights where each bulb is a bit, because the bulb has two states, off and on, 0 and 1. Once I encountered this Christmas string light analogy, it all made so much sense to me, so I was so excited to get to this. Bitwise operators are like the switches you use to control which lights are on and off. You can combine switches, like the AND operator, light up more with a single switch, with an OR operator, flip all the lights with a NOT operator, or even make sure only unique lights are on, aka our XOR operator. And think of the shift operators, the ones at the bottom there. They're like sliding the string of lights left or right so you can create different patterns. It's all about manipulating those lights to create that dazzling display you gotta have on your house or your Christmas tree, or whatever you're using string lights for. It doesn't have to be a holiday. Like, people put string lights up around like their streaming rooms and things like that. I mean, like, I think like the quintessential American male college dorm is, I don't know how to decorate this place. Let's put up some Christmas tree lights around the door frame or something. But nevertheless, that analogy hopefully helps you understand how to look at a number and how these operators can help you manipulate it. So let's talk about XOR in particular. Okay, so XOR in particular, let's go ahead and actually switch to this as well now that I'm here. Really, I can't zoom in on the picture? How annoying. That's how you do it. You click. Okay, so I should know that given how often I use this. I will attempt to remember to put this in an Imgur link and put it in the description below. I'm saying this out loud for future uploading, editing. Luke, to remember to do it. We'll fix it in post, guys. No worry. So, like I said, the definition of XOR in particular, it compares two binary digits and yields one only when one of them is 1 and the other is 0. If both are the same, it gives back a 0. Okay, so that's your technical definition that you want to probably memorize or be able to write down. To think of it as an analogy, think of it as a conductor at a set of crossroads. So the XOR is the conductor at a set of crossroads, and it's making the decision at those crossroads. Then let's say we have two friends that come up to XOR at this crossroads, and they're named Bit and Byte. And let's say the XOR conductor says, if one of you goes left and the other goes right, I'll be happy. But if both of you choose the same path together, or if you completely stand still, then I ain't gonna let y'all through. It's all about being exclusive in their choices. So that's what our analogy is gonna be. It's a conductor at a crossroads. They have to go to separate paths, all is good. If they choose the same path or completely stand still, then XOR will not let them pass or do anything for that matter. It'll be unhappy, right? So that means when you're comparing numbers, here's what it looks like. Remember, we are dealing with bits here, so zeros and ones. So this right here, this little table, will be handy in you solving the entire thing here, believe it or not, because it took me forever to understand how useful this table of numbers really is. And I should mention, if you ever see diagrams, this is what a XOR gate looks like. You have two inputs, A and B, aka bit and byte, come to a crossroads, and you get A or B depending on whether it's exclusive or not. Remember, the exclusive choice is the whole thing here. So this is what you might see as a diagram. If you see that, you got yourself a XOR. So these are the examples. If we XOR 0 is 0, they are the same, therefore we end up with 0. If we XOR 0 and 1, they are different, therefore we get 1. If you XOR 1 and 0, so you see the order of operations, hint, hint, the order of operations of two numbers that are XORed together do not matter. They have the same result, which is 1. Then we get a number XORed with itself, kind of like 0, also results in 0. So this is how your table breaks down. So remember, 0 and 1, they are different, therefore we get 1. Same thing with 1 and 0. They're still different, even though their order is different, right? They're still different, therefore we get 1, and we're still good. But if we XOR 1 with 1, or 0 with 0, we get 0 because they're the same, right? So that's what we're looking at here. So the important properties of XOR is that it's like a mirror. It has identity. Whatever number you hold up to it, you get the same number back, right? So if I have 0 changes to my original, I stay the same. So that's why if you get 5 XOR 0, you always get 5. It's like holding up a mirror. It is self-inversing, meaning a number, if using XOR on a number with itself, it's like pressing a reset button. It always gives you 0, right? So a number XORed by itself, so 5 XOR 5 would still be 0. 6 XOR 6, it's still 0, right? Think of it like two identical twins arguing until they both go up and go silent, the 0. So if you ever see a number XORed with itself, it's 0. The important part is that it's commutative. Commutative, I think that's that word. the commutative in that the order doesn't matter, right? It's like putting on socks. Whether you put on the left one or the right one first, you end up with 2 feet covered in socks, so it doesn't really matter what order you do them in. The end result is the same. You got 2 socks on your feet, which is what this represents right here, right? So, like 2 XOR 3 is the same as 3 XOR 2. In this case, 0 XOR 1 is the same as 1 XOR 0. Doesn't matter. And it's associative, meaning no matter how we group them, no matter how many set of parentheses or additional, operations we put in between things, the grouping does not matter. So you cannot change the order of operations like you would in arithmetic with parentheses signs to say, hey, do these first. It doesn't matter. It's like a relay race. No matter the order of how the team members run, the total time is their cumulative effort, their collective effort, right? So like I said, if I had additional numbers here wrapped in parentheses, and I move those parentheses around to try and affect the order of operations, it doesn't matter for the XOR operator. So with this diagram handy, I'll probably click back to it every now and again to try and help y'all figure this out. Let's find out how and why specifically this dumb little thing works, because I still think it's kind of like magic when I look at it myself. And let's go ahead and try and analyze step by step how this works. Then I'll get into big O and how this is actually useful in the real world other than flexing on your interviewer, which again, I think learning something for the sake of learning something is always fantastic. You can't go wrong there. Learning something so you can potentially, if the opportunity presents itself, flex on your interviewer and show that you really know your stuff, even better. That's like icing on the cake. And then third, actually knowing how this can help you in the real world, always kind of nice too, right? All right. So let's break this down and see how it works. And I promise you that this explanation is what, along with the Christmas light analogy of understanding Bitwise, the diagram and the little example table I gave y'all and the analogy here of XOR is all fine and dandy, but let's see how it actually works on these numbers, because that's where it gets a little bit different. And I'm, like I said, breaking this down into a step-by-step procedure. Was I really that zoomed out? No, I was zoomed out because of the diagram. That's right. Okay, so let's go ahead and break down each iteration of result and num, run their comparison, and then we'll find out if it really does result in 3 at the end or not, or if this console log is lying from a different file somehow. Okay, so on iteration 1, we have a result of 0, and our first number we're iterating over is the number 1, so our num is 1. Now, these are JavaScript integers, and they're going to be displayed and operated upon in binary. So I'm going to choose an arbitrary number of bits to display 0, because technically 0 is just 0 in binary, right? Binary of result. And then the binary of 1 is, no surprise, 1. So we're going to say binary of num. So result of 0, num 1, this is representation. I am arbitrarily going to put 3 places or 3 bits of space. Now this could be as long or as short as needed to be depending on whatever the maximum JavaScript allows us. I don't remember off the top of my head. But I'm going to make it 3 just so you can see how this runs here. And there we go. These are the binary representations that this XOR operation is going to do. So basically what's going to happen is the following. Let's run our XOR logic on each one of these. Now remember, 0 and 0 gets us 0. So we're going to look at the first column and say 0 and 0 are going to be, surprise, 0. 0, 0, the second column right here, is the same thing, another 0. A 0 and 1, those are different. So 0 and 1, those are different, which gets us a 1. So we're going to go 1. And that right there, like we see right up here, is the binary representation of 1. So result has a value of 1. There we go. That's our first iteration. Let's go to our next iteration. For simplicity, let's copy and paste this. Result is 1. The next number we iterate on is 2. So there we go. The binary result of 1 is that, and 2 is the following. So remember, this is how you count in binary, right? So let me show y'all here. 0, 1, then to get to 2, you move up, because, again, we're not in a base 10 system where this goes to 1, 2, 3, 4, 5, 6, 7, 8, 9, then the next number ticks. This is binary. We have 2 counts only. So instead of going like 0, 2, 3, 4, 5, 6, 7, 8, 9, and then you get to 10 in base 10 numbering, we only have 2 options, 0 or 1. And well, we just already used the 1, so this has to go to 0, then the next number in the series ticks. So this is not 10, this is the binary number of 2. Then this would be 3. And then to get to 4, we tick the next highest number, and then the other 2 back down to 0. And that's how it ticks up. You can find animations online of counting to 10 in binary, and you'll have a great little like analog clock style representation of these numbers flipping. But that's how you count basically in binary, and that's what we're doing up here in these result values and number value representations. So result is 1, so 0, 0, 1. Num is 2, so 0, 1, 0 is the binary of the number 2. Let's do the XOR logic now. 0, 0s are the same, therefore we still get 0. 0 and 1 are different, so we get 1. 1 and 0 are different, so we get 1, and our result here is 3. Here we go. Next iteration. Result is 3. The next number we iterate over is a 3 itself. So we're going to do result 3, num 3. So we're going to get 0, 1, 1 is 3. That took me a second there. Let's just copy and paste this. Boom. 0, 1, 1 is result, and num is also 3, so 0, 1, 1 for both of them. So here's what we learned. If they're all the same, it zeroes out. Because remember, oh, I can't alt tab. There we go. All zeros is still 0. All ones are still 0. Remember, they're all the same. That's the big logic in the table here. So if they're all the same, we just get a bunch of zeros, which means our result is our friend 0. So our next iteration will be result 0, and the number after 3 we iterate over is 1. Okay, so there's our result. There's our number. So binary of 0 is 0. Binary of 1 is 1. We're going to run our XOR logic on each column of numbers. Same, same, different. So our next result is 1 as I speed things up a tad here. All right, y'all can see where this is going. Result 1, num, I believe 2 is the last number we're iterating over in our array. So we get result 2, or result 1 from the previous iteration, a num of 2. So 1 is represented by 0, 0, 1. 2 is represented by 0, 1, 0. We run our XOR logic on it, and we're going to get same, different, different, which our result ends up being 3. That is the final iteration of our for loop, which means the last value in result is what we return. Return result, which ends up being 3, as we can see right there up in the console log of this particular test. So hopefully that breakdown, that again was one of my bigger aha moments when I wrote it down myself, and I was like, whoa, it does work. But why does it work? Remember that big thing about the properties of XOR, right? If it's the same, it's always 0. So as long as an even number of each pair of numbers appears, right? So 2 1s, 2 2s, and an odd man out. So if I add 2 more 2s, it still works. But if I only add 1 more 2, then it fails. So that's the big note on this algorithm and why it works that way. Because with XORs, they cancel all repeated numbers in an even number of times, cancel themselves out, because remember, any number XORed with itself is just 0. So you can think of that as, oh, any number XORed with itself will eventually give us a 0, canceling itself out, and that leaves us only with the possibility of the one remaining number that is not repeated. That is how this works with XOR. So in terms of big O, why is this so awesome? It has both a time complexity of big O of n. The bigger our array is, we're going to have to iterate over at least one time. So it's going to be a linear. It's going to be a linear big O for time complexity. The larger the array is, the more iterations we have to do. But the big benefit of this one compared to the object map version, which again would be, key 1 appears twice, 2 appears twice, 3 appears one time. Compared to the map version, that's an object. That is a data structure that will grow also based on the size of our array. So in this case, we don't have that. We have a simple number that we are storing that's not going to grow, meaning it has a space complexity, big O of 1. And that's what makes this algo so awesome to know if you find the specific input that you're working with that can be solved with this. It gives you a big O of 1, meaning it's a flat line space complexity of just 1. And that is incredibly space efficient. And again, because this is doing something at like the CPU level, a bitwise operation, it is extraordinarily speed efficient as well, and very, very awesome to know how to do. So in summary, hopefully, the breakdown of we can do some of the other ones here just to point out that it still works. I mean, I'm not breaking down this entire comparison to break down all these bigger numbers like I did down here. You could do that on your own if you're not convinced it works. But again, the point being, as long as I have a pair of repeating numbers over and over and over again, and then one different one in the list, in the array somewhere there, it will find it, because the rest with XOR cancel themselves out, and we are only left with the one that can't cancel itself out. And that's how this one actually works under the hood. So hopefully you'll have a better idea of Bitwise, bit manipulation, and how XOR works, and how it can work in this kind of algorithm, right? It can lead to solutions that are very elegant but insanely efficient. It's kind of a peek into low-level operations, like it's closer to computer language than JavaScript is, right? That happen inside of our computers, inside our devices every single day. So in an interview, bit manipulation questions really test your ability to think at the lowest levels of abstraction in programming. And your understanding of these concepts can really set you apart from the crowd. Trust me. I mean, I waited this long to actually use them, but they are awesome. They really are. Now that I actually understand them, they're awesome. So hopefully this gave you some understanding too. So you'll see these a lot, like in cryptography and things like that. Error detection, correction of data transmission. It is a incredibly low-level tool that you will be surprised to find in a lot of really crazy solutions out there, right? So yeah, that's our bite-sized look at bit manipulation. So if this video helped you understand and appreciate the bit level operation of XOR at the very least in JavaScript, do the meme, smash the like button, hit subscribe, hit the bell notification for future videos in my little mini Bitwise series here. I've got more coding insights and the other Bitwise operators coming your way, and you won't want to miss out. Remember, coding is not just about writing functions, it's about writing stories in a language that your computer can understand. So keep telling those stories and keep them efficient. Until next time, never stop learning. And this is Luke, signing off from Covalence.